Hello, Physical Science. This is Mr. B. We are starting today with Chapter 14, and the title of this chapter is Work, Power, and Machines. So I would definitely write that down. That may or may not show up as the first question on a quiz. So that's just a little introduction about what this chapter, just the title, and it'll make more sense if we actually just dive into the first section, because the first part of that section is dealing with the first two components, and that is work and power. So we're going to take a look at that. These are words that you've probably used many times in your life, but from a physics standpoint, work and power have a very specific meaning. And we can only use them at certain times because based off of those specific meanings. So we'll jump right in, again, as usual, with our little introductory example. This one is a weightlifter. So if you hear the words work and power, I could think that's pretty logical to relate a weightlifter to that. So it says the weightlifter over there applies a large force to hold the barbell over his head. So yeah, obviously looking at that, it's going to require quite a force in order to get that up to that point and to actually hold it there. He is exerting an upward force on that weight to keep it up there. However, because the barbell is motionless, he is actually not doing any work on the barbell. So even though he is holding it, and again, in the maybe the everyday sense, we would assume that, yeah, he's doing a lot of work in order to hold that barbell up. But from a physics standpoint, from our technical definition of work, he is actually doing no work whatsoever. And we're going to explain why that is true here momentarily. And in order, so one of the big key questions is, when does a force actually do work? So in science, work is the product of force, so actually a push or a pull of an object, and distance. So distance is the big kind of new component there in order for work to actually be done in the terms of a physics standpoint. So I definitely have that definition written down as well. And then again, just to kind of restate some of the bigger key points here, for a force to do work on an object, some of the force must act in the same direction as the object moves. So if there is no movement, no work is done. So since he is holding that barbell stationary above his head, there was no work being done. And any part of a force that does not act in the direction of motion does no work on an object. So it might have taken some work to get the barbell up to that point above his head. He was doing work kind of in the process of lifting it up, but as he's holding it, no work is being done because the object is motionless. And then this is our next one, just going to explain this a little bit more, because again, it kind of seems backwards that, okay, yeah, you're holding it up there, you're obviously doing work to keep it up there, but from a physics standpoint, that is not true. Because work is done when a force acts on an object in the direction the object moves. That's the big thing. It has to be in the same direction that the object moves. And then work is done when the weightlifter exerts an upward force to raise the barbell, which I just said. So for the first part of his motion, when he's raising the barbell, he is doing work because the barbell is moving in the same direction that his force is moving. So that's the first part of work. So he was doing work at one point. However, the weightlifter does no work on the barbell as he holds it over his head because the force applied to the barbell does not cause it to move. So in order for work to be done, again, I'm going to sound like a broken record here, but there has to be motion. That's the big thing for work. There has to be motion in order for work to be done. And there's kind of some different ways that we can measure this. First off, if all of the force acts in the same direction as the motion, all of the force does work. So if you're moving if you're pushing a box across the floor and your motion is in the same direction as the force, then all of that work goes towards the force. However, if only part of your applied force acts in the direction of motion, that part of the force does work. So you can kind of have a split there where some of the force you're exerting is doing work on the object, or some of the force is not exerting work on the object. And we're going to see a couple examples here momentarily. And if none of the force applied in the direction of the motion, then the force does no work. So these are all pretty important. These are basically the breakdowns of when work will and will not be done, and we can kind of have one in between. And so these next couple slides are going to kind of illustrate that. So we have our first option here, letter A. The woman there, she's pulling her suitcase across the floor, and you can see her red arrow indicates the force that she is moving, and then this little black arrow is the direction of motion. So the suitcase is moving straight to the right here, her force is acting in that direction, so her force and motion are in the same direction, so she is doing work. All of the force she is exerting is doing work on that suitcase because it is moving in the same direction of motion. Then now our second option, we can look at this red line here. This is the direction, so now she's kind of dragging it, she's pulling it with her handle, kind of like how the suitcases are designed to be used, and our force is kind of in a diagonal, and our direction of motion is still the same way. But if we look, there's a portion of the force that does work, and then there's a portion of the force that does not do work, because remember, force is a vector, so we can kind of break it down to even smaller vectors. Again, we did the Pythagorean theorem with all of our velocity and those types of problems, so it's kind of the same thing here. So in this example, part of the force is doing work on the object because part of the force is going in the same direction as the object, but this upward force is not. So, and then our last example is when there is no work being done on the suitcase. So probably the most effort here, her force, she's holding the suitcase up by its handle. Her force is holding up, but she's walking forward, so that force is not acting in the same direction as the suitcase is moving, so no work is being done here. So we can look, force is going up, motion's going to the right, so we can, again, this is probably the hardest situation for her, but in terms of physical science, in terms of physics, she's actually not doing any work. So the best way to break down work is it has to do with force and direction of motion. They have to be going in the same direction, or at least part of the same direction, in order for work to be done. And because of that, those two things, we actually can calculate work. So if we did example problems, work is simply force times distance, which kind of actually makes perfect sense because that's the only two things we've been mentioning so far when we talk about work. So that's our equation for work. We'll probably do some sample problems with that later on. And when we use our SI units in the work formula, force is measured in newtons, which we should know by now, and distance in meters, which we've done that before, and the joule, so here's a new term for us, the joule is the SI unit of work. So when we talk about a joule, that's the SI unit for work, and it is equal to 1 Newton meter. So that's probably our newest SI unit. Again, we should know newtons by now, we should know meters, so when we talk about work, it is measured by the joule. So if we ever do some sample problems, just keep that in mind. That's going to be the joule. And then I think our last slide here is, again, a really simple sample problem. It says a weightlifter raises a 1600 Newton barbell to a height of 2.0 meters. We just take the force times the distance, and it's just 3200 joules of work being done. Again, that's about as simple as it gets right there. So, yep, that was it for our first video. Let me know if you have any questions.